Okay, I have introduced different types of models, right? 5 types of models in the last 2 video clips. And here in this video clip, I would like to talk about how do we use simulation models. In other words, um, what are the purposes of simulation models? Okay, in general, there are two purposes. It's either prediction or learning. Okay, so for prediction, usually we need to have rich theory and rich data to finish prediction, which means that we need rich theory, reliable theory to create reliable model. And based on that reliable model, we need a large amount of data to make sure that our prediction is also reliable, is data-based. But that's the perfect scenario here. The theory is reliable and we have a lot of data to experiment. But if that is not the case, usually that is not the case because doing high quality prediction is hard, right? You need rich theory and rich data. Usually we have either have rich theory but poor data, or poor theory but rich data, or poor theory and poor data, depending on your scenario. If you have rich theory but poor data, determine critical data shortages. And then you need to collect more data to finish the prediction. And this is the 3 scenarios, they belong to the purpose of learning, because in these scenarios, you cannot do prediction, okay? If you have a rich theory, poor data, okay, you know that you need more data. If you have poor theory but rich data, you need to use this rich data to develop new reliable theory. That's what you are going to learn, okay, from experiments and the process of creating models. If you have poor theory and poor data, sadly, develop new theory and determine necessary data. You have to do both, okay? You may want to create an unreliable model based on this poor theory and begin to collect data, right? And do simulation iteratively. And in this process, you create more reliable theory and collect more data. And eventually you want to have a reliable theory and reliable data to finish the prediction. So here is a figure showing you different types of models in this understanding versus data space. If you have very good understanding, your model is somewhere here. It means that your theory is good. If you have very poor understanding, your model should be here along the horizontal axis. It means that your theory is bad. On the other hand, if your data is good, you have a lot of data, high quality data, your model is here along the vertical axis. If you don't have enough data, the data quality is poor, your model is here, right? Is here along the vertical axis. So using data and understanding, you can locate a specific type of model in this space. And if your understanding and data, they're both poor, your model is a learning model. If your understanding is solid, your data is pretty good, your model is somewhere here. Your simulation model is somewhere here. It's ready for prediction. It's ready for prediction. And yes, we prefer to use models for prediction. It is natural to want to use models for prediction, but there are reasons to be careful before carrying out prediction. So firstly, lack of data or understanding. Prediction can do more harm than good. It means that do not jump to prediction so quick. Before that, make sure that your theory is reliable, your data is good enough, your data set is large enough, your data quality is high enough. And be careful with complexity and emergent behavior. Emergent behavior is something standing in the core of this course, of this class, emergent behavior. Okay, I'm going to introduce it later. Well understood individual elements and good data. Aggregation of many interacting elements can lead to unexpected nonlinear effects. These effects are called emergent behavior. It means that, okay, you are very clear about each individual's behavior. Okay, you have very good knowledge on individual level. But sometimes in real world, when these individuals, when they aggregate, when they behave together, you will see something unreasonable or cannot explain by individual behaviors. This type of collective behavior is called emergent behavior. Okay, that's very important to this course. And models as guides to data collection. Okay, which data are most critical to improve our understanding? It means that we have some theory. They're not necessarily perfect, but solid. And so we use this theory and we create models, simulation models, to guide us on collecting data. Okay, so we do sensitivity analysis. To be discussed in chapter 7 of the text. In this semester, we do not have time for as far as chapter 7, but if you are interested in it, after this semester, when the semester finishes, you can go there, okay? Systematically vary the parameters to determine which parameters have strongest effect on outcomes, which means that when we're using models to guide us for data collection, we will have to choose some variables because there could be multiple variables you can collect, but you don't have the resources to collect all of them. So you want to find out which variables are most important. Okay, which variables affect outcomes dramatically. Okay, or in other words, outcomes, you need to find out which variables that your outcomes are sensitive to. You want to find out all those variables that your outcomes are sensitive to and use them as your input. And in that logo, there is something called behavior space. This is something you're going to use in lab 7. That's the last lab of this course. You're going to use it for setting up experimental design for non-local models and find out which inputs, which variables are most valuable to your models. And models as tools for thought. So simulation equals theory plus experimentation. Okay, so when we use simulation models, they represent current working theory, but experimentation is another thing. It refers to exploring the implications of the theory in the real world. Okay, so we have a simulation model, we run it multiple times to see the possible outcomes of the phenomenon in the real world. And this phenomenon should be able to get addressed by this simulation model, And when we use simulation models, there is another problem very important that you need to be careful, okay? It's called the equifinality problem. It means that there could be a large but infinite number of possible models, including the same model with different input data could be consistent with an observed pattern, which means that for a specific observed pattern or phenomenon, a lot of models can be used to address it. Okay, so this makes identifying the processes responsible for the pattern difficult, And when there are multiple models can be used to verify, to be consistent with a pattern, it means that, okay, there are multiple processes related to this pattern. Each model can be considered as a process that is consistent with the pattern. But now we have multiple processes associated with the same pattern. Which one is the correct one? Which one actually caused this pattern? That is a huge question mark. Okay, this equifinality problem makes problems of model selection and inference, which means that you need to find out a specific method or methods to interpret these models and to find out which model should be selected to address this pattern, which model, which process represented by a specific model is responsible for this pattern. You need to find out that among a lot of simulation models. Okay. Okay, I will stop here. This is the end of section 1.2 of chapter 1. I will see you in the next video clip. Thank you.